In this video, we'll discuss gradient descent with momentum. In particular, we'll talk about how we can use momentum to solve the problem with the parameter we are optimizing being stuck on saddle points, being stuck in the local minima. Let's talk about momentum. When learning momentum, it is also helpful to learn about the concept of position, velocity, and acceleration. Here, x denotes the position of our red ball. The initial position of this red ball is given by x superscript 0 is 0. The ball is accelerating. We have an acceleration denoted by a and time denoted by t. We can get the new position by using the displacement acceleration equation, plugging in the value of our new time, and we get the position of 6. This new position is given by x superscript 1. Tracking the position of the red ball is similar to performing gradient descent. We have the acceleration term in yellow and the displacement term in red. We have the kth iteration of our parameter. This is the kth position of the ball. If we have our acceleration term, this is like our gradient. The next iteration of our parameter is the position of the k+1 iteration. Everything we are doing for the displacement acceleration equation, we can apply to the gradient descent algorithm. Velocity is the rate of change in position with respect to time. Let's look at the case where the velocity is constant. We have a velocity of 3 and a time interval of 2. We can calculate the new position of the ball with the equation of the old position and incrementing it with the product of velocity and time. We get the new position. This is similar to the update rule for gradient descent and momentum. Let's review the equation for velocity with constant acceleration. The velocity of k+1 is the velocity at k, plus the acceleration multiplied by the change in time. The velocity term here is used to update the weight when we perform gradient descent using momentum. We use the momentum here to calculate the velocity, which we will use to update the weight. The velocity at the k+1th iteration is a sum, the derivative of our cost or loss function with respect to our weight, and the sum of the velocity of the previous iteration multiplied by the momentum. The momentum term represented as the Greek letter rho. It's a positive number, usually less than 1. We set our initial velocity to be 0. The way for the k+1th iteration is updated with the previous weight minus the learning rate multiplied by the current velocity. This is our learning rate, as represented by the Greek letter eta. Here we show that updating our weight with momentum is similar to updating the position of our ball in the presence of acceleration. The derivative of our loss function with respect to our parameter is analogous to changing in velocity, taking acceleration into account. Then we have our parameter weight. This is analogous to changing the position of our ball given the time and current velocity of the ball. We start off with our initial parameter value. We add some velocity. The new position of our ball is similar to the new value of our weight. We can think of momentum like momentum in physics. The parameter rho is like the mass of the ball. The derivative of the cost or loss is like the force. When we have an object with a small mass which is equivalent to a small rho, the product of momentum and the previous velocity is small. Adding the derivative of the cost or loss is like adding a force in the opposite direction of the ball. If these two values are equal, the sum of these values is 0. If we have a relatively large object, it'll take a relatively large amount of force to stop it. A small value for the gradient will not stop the ball. Now, let's see how momentum can help us solve problems with optimizing neural networks. Let's review saddle points. Saddle points are basically a flat point in the surface, and for these videos, we're going to mainly focus on one-dimensional saddle points. These problems get exceedingly worse in higher dimensions, but unfortunately, we can't really visualize them. Let's use an animation of a ball to represent gradient descent. The horizontal direction represents the value of the weight in which we are optimizing, and the vertical direction is value of the cost. We'd like to determine a value for the weight that minimizes the loss function, which can be visualized as a ball rolling down to the bottom of the hill, giving us a new value for the cost and weight. When using gradient descent, we can calculate the gradient. This is similar to how gravity causes the ball to accelerate down the hill. We update the parameter value. Using our ball analogy, the ball will roll down the hill, representing the change of parameter. Now let's assume we're at this point. The curve for our cost is flat. As the curve is flat and our gradient is zero, when we perform gradient descent to update our weight, nothing will happen. We will get stuck on the saddle point. Let's see how momentum helps us overcome this. Using momentum, we'll start at this point and we'll calculate our first iteration for the velocity. We calculate initial velocity. We will perform our parameter update. We call the velocity with the learning rate. We continue for the next iteration. We add the gradient of the cost function to the previous iteration of our velocity. We update the parameter value. The momentum helps us achieve a high velocity in the region where the graph is flat. At this point, the gradient is zero. We update the velocity by adding the gradient. Even though the gradient is zero, the current velocity is the product of the previous velocity scaled by the momentum. This allows us to achieve a non-zero velocity for the current iteration. This allows us to move the ball along the axis of the parameter w, even when the graph for the loss is flat. We will continue this process till gradient descent allows us to reach the minimum value of the loss. If we pick a momentum term that's too small, we will get stuck in the saddle point. We can perform cross-validation to check a momentum term such that we won't get stuck in the saddle point. In the lab, we run several iterations of stochastic gradient descent with momentum and plot the results. We see the parameter values do not get stuck in the saddle point with momentum. Local minima is another problem that gradient descent with momentum helps us overcome. We have a cost function. There are 2 points where the gradient might be zero. Using our ball analogy, we have the global minimum. This is the point of the function where the cost is the smallest. We have the local minimum, which is the smallest point in a small neighborhood. This is where the ball stops rolling. We would like to use momentum not to get stuck in this local minimum. At the local minimum, our derivative will be negative. Using our ball analogy, it will force the ball to roll in the direction of the local minimum. But in this case, the velocity term for the momentum is in the opposite direction. If the momentum term is too small, the ball will get caught in the local minimum and not reach the global minimum. A good value of the momentum term should allow us to reach the global minimum. If we select a momentum term that is large, we may overshoot the global minimum. In the lab, you can experiment with different momentum terms and see how you get caught in a local minima versus global minimum. There are other problems the momentum will help you solve. Check out the labs. In PyTorch, we just add the momentum value in the parameter of the constructor for the optimize object. In the lab, we will use the spiral dataset. Each color is a different class. In the lab, we examine the total loss or cost we see that a momentum term of 0.5 performs best for our model.